All right, part 2, notes on currents in the core and mantle. Generally, the hotter something gets, the less dense it is. Things generally are going to expand, and so they sort of get fluffier and less dense, sort of. The cooler something gets, the more dense it is. Generally, when things get cold, they contract. You can think about huddling up when you're cold and you're grasping your arms close together. You are contracting your body to save your heat. Okay, most objects will contract when they get cooler, and that gets them more dense. And because of the greater density, cooler materials will sink below the hotter materials. Modern theory of Earth's magnetic field is that the liquid that's in the core is swirling, and part of the reason is because of this different temperatures, partly due to convection currents where hot stuff rises and cool stuff sinks, and it's partly due to something called the Coriolis effect. We haven't studied that, but it's because of the rotation of the Earth. So the moving liquid that is going in these convection currents is carrying charges. And when we have charges that move around, they create a magnetic field. The North Pole of this magnetic field is not actually the same as the geographic North Pole. If I looked at a globe and I spun it, the post that is holding the globe onto the frame, that's the geographic North Pole. That's where all the circles are going around and around and around. That's not where our compasses are actually pointing. Our compasses point a little bit off because these currents that are in the center of the Earth aren't exactly lined up quite right. If you looked at the compass really carefully, you'd see that it is actually pointing to a spot right about there, a little bit north of Canada, north of the islands. Years ago, when I first taught this, it was actually on one of the islands, but it's slowly moving around and moving closer to the North Pole. Earbud, please. Currently, the magnetic North Pole is a few hundred miles away from the geographic North Pole. North of Canada. So if you're over here in Alaska, north is this direction, but the magnetic North Pole is actually to your east. Compasses in northern Alaska point east. That's kind of strange. So when you are a serious hiker, you're really trying to get across the wilderness, you got to know the difference between where the compass is pointing and really true north to the geographic North Pole. Currents these currents that are in the core that cause the magnetic pole, the currents can change direction, so the magnetic field can change. It's currently moving towards the geographic North Pole. 100 years ago, the magnetic pole was moving about 15 miles per year, but now it's moving 55 miles per year. Not miles per hour, miles per year. We don't know exactly why. Okay, so the magnetic field is shifting, it's changing. It can also change in another way. The field can even flip directions. There's evidence of the magnetic filings of some rocks that indicate that compasses would have pointed to the South Pole thousands of years ago. The magnetic field has gotten also weaker. Not only does it flip, not only does it wander around, but it can get weaker and weaker. It is 85% as strong as it was just 200 years ago. So all of these can change because the currents in the core change. When the currents slow down, it's going to get weaker. When the currents change directions, the magnetic field either flips or wanders around the ocean in the north. You can see here in the pictures how much it's moved over the years. I started teaching here around 2005. It's moved from there way up to there just in the time that I have been here, and when I first started teaching, it was way down here on the islands. Okay, now, Those or the magnetic field is due to the currents in the outer core. There are currents in the mantle too. The mantle is also moving in currents that look like a circular conveyor belt. It moves about an inch a year, maybe a foot per year. At this rate, it would take tens of thousands of years for a material to take one loop. The heat that drives these currents may be partly due to radioactive elements. And it might be due to the heat left over from the origination of the Earth. But the material in the mantle here is really thick. It's like Play-Doh. If you just have a hunk of Play-Doh and you plop it on the table, it's going to hold its shape. But if you squeeze it with your open fingers, it's going to flow through your fingers, and it'll flow. You could push it through a pipe if you were really pushing hard. So that's what the mantle is like. If you don't push on it, it's basically a solid. So let's draw convection currents. Down here, would you please draw something along that lines, like that? And it's the cooler material that sinks down towards the center. And it's the hot stuff that rises. So that happens in the mantle there, the second layer down. And it also happens in the outer core. Please label one side cool and one side hot. Hot stuff rises, cool stuff sinks, creating the circular current called a convection current. And that happens all over the place. Here we'll have another one like that. Again, cool stuff is sinking and the hot stuff is rising. There are some places where the material in the mantle is moving upwards more like a fountain than a conveyor belt. These are called plumes. Hawaii is an example. So that is all about the currents in the core and the mantle. We're next going to do a project and then some homework.